Hi there, and welcome back to MA211. Today we're going to talk about convolutions, what they are, how to Laplace transform them, and how to solve equations involving them. So first of all, the convolution of two functions is a new function. So just like the Laplace transform of a function is a new function, the convolution of two functions is a new function. And so here we have a definition of how to compute what the convolution of two functions is. So this symbol here, f star g, that's not multiplication, that's convolution, and you read that f convolved with g. So you get a new function and it's called f convolved with g when you do this. And this definition here, again, that's how you calculate the convolution of two functions. So f convolved with g is this integral from 0 to t, f of t minus tau, g of tau, and then the integration variable is tau, so you end up with something involving a t. So you start with two functions of t, you end up with a new function of t when you do this. It turns out that f convolved with g is the same thing as g convolved with f, so it doesn't matter. You can go ahead and put this t minus tau into the f, or you can put it into the g when you're doing the integration. It doesn't matter which way you do. You usually just put the t minus tau somehow into the simpler of the two functions to make the integration easier. Okay, so let's do a quick example. So if f of t is just t and g of t is e to the t, then let's compute f convolved with g of t. So f convolved with g, I'll write it as f of the integral from 0 to t, f of t minus tau times g of tau d tau. So I plugged my t minus tau into t and got t minus tau, and I plugged tau into e to the t and got e to the t, or e to the tau. And now I just have to do the integration. I decided to split it into two parts, and now this one, remember this is a integration with respect to tau, so the t can just come out of the integration, and here you'll have to do integration by parts. You have an integral of t minus, or tau minus e to the tau. So you do the integration by parts here, and you end up with this thing. Since tau is the variable of integration, all the taus should be gone, and you get this expression, and this is the function. It's a function of t, and this is t convolved with e to the t. This is an expression for that function. Okay, so you should probably really do a couple of these calculations just to get comfortable with what a convolution is, how it's defined, and so on. Okay, so I told you that it doesn't matter if you put the t minus tau into g or you put it into f, and here I'll just do an example demonstrating that, well, maybe he's correct. So the same f and g as last time. This time I do g convolved with f, so that means I would put the t minus tau into g. So I would plug t minus tau into e to the t and get e to the t minus tau, and I plug my tau into t and just get a tau, and do the integration. Again, you'll need an integration by parts, and it all works out. You get the exact same expression. So this guy is e to the t convolved with t, and yeah, really they're the same thing. I promise it doesn't matter which you do. I guess this time maybe it was a little easier to put the t minus tau into the e to the t, but neither one was very hard. Okay, so if you're given two functions, you can compute the convolution of the two. Here's another example. If you wanted to compute t convolved with t squared, so this is your f and this is your g, okay, it would probably be a whole lot easier to put the t minus tau into t, because then I'll have a t minus tau squared. And if you write it the other way, the other thing you could do is say this is the integral from 0 to t, and put the t minus tau into the t squared, so you'd have tau and then t minus tau squared d tau. And then to do this integral, you'll probably just go ahead and FOIL out this thing. I mean, it'll work out just fine. It's probably easier to put the t minus tau always into the sort of simplest function that you have laying around. So that's why I did it this way this time. So t convolved with t squared turns out to be 1/12 t to the fourth. Okay. So that's how we compute a convolution. The thing we're really going to want to do a lot of the time is recognize these integrals as convolutions. So here, how do I write this as a convolution? This looks like the integral from 0 to t of, this is e to the t with t minus tau plugged in, and this is cosine t. So this one is e to the t convolved with cosine t. Here. Now here it looks like I have the function t, which I plugged a tau into, and here I plugged a t minus tau into what? Sine 4t. Right? I went ahead and plugged in t goes to t minus tau, and then you'd get sine 4t minus 4 tau. So this guy is t convolved with sine of 4t, or sine 4t convolved with t. It doesn't matter which way you write it. So this one looks like I have t to the fourth with t minus tau plugged in here, and this one is just t. Oh, oops, that's t, not tau. This one over here, this is t, and I plugged a tau in for t there, so this guy is t to the fourth convolved with t. Okay, so if you have these integrals, many times you'll want to recognize them as convolutions. Okay, so now what's so great about these convolutions? Now remember that f convolved with g, if these are two functions of t, then f convolved with g, that's a new function of t. And I might be interested in Laplace transforming that function of t. And it turns out that if I want to Laplace transform f convolved with g, then all I really need to do is Laplace transform f and Laplace transform g and then multiply them. Okay? So the important thing here is that this guy is convolution. That's the convolution symbol. This is plain old multiplication. Okay? So we've talked about this before. If you have two functions of t multiplied, it's not true. You can't Laplace transform. The Laplace transform of f times g is not the Laplace transform of f times the Laplace transform of g. That does not work out. Okay? And many of you know that already, and you don't make that mistake. But what you do is this: you'll have you'll have two things multiplied in the s domain, and you'll want to inverse Laplace transform them, and you'll just do this: Laplace transform of the first, or inverse Laplace transform of the first one times the Laplace transform of the second one. So, for example, the inverse Laplace transform of like 1 over s squared plus 1 times, say, Laplace transform of 1 over s minus 3, right? That's not, if you want to inverse Laplace transform those, remember what you do is a partial fractions decomposition, and go from there. What you don't do is inverse Laplace transform this one, right, and get sine of t, and then multiply it by the inverse Laplace transform of that one, which is e to the 3t, right? So if you have two things multiplied in the s domain and you want to inverse Laplace transform them, you absolutely do not just inverse Laplace transform each one and then multiply. However, what you can do is say, well, the inverse Laplace transform of f of s times g of s, it's the inverse Laplace transform of f of s convolved with the inverse Laplace transform of g of s. So what is correct is that you could say, well, this is sine t convolved with e to the 3t. That's correct. So suppose you ran into this thing here and you wanted to inverse Laplace transform it, you would be perfectly correct to instead of doing partial fractions, say, well, this is sine t convolved with e to the 3t, and then compute the convolution. It's usually more work to compute the convolution, so that's why we don't go to that right off the bat. As you saw above, these convolutions are sort of a pain to compute. But you are correct, and I'd have to give you some partial credit if you said that it's sine t convolved with e to the 3t. That is correct. Okay, so let's just do some examples. The Laplace transform of sine 3t convolved with e to the t, well, that's just the Laplace transform of sine 3t times the Laplace transform of e to the t. And that is, what is that? 3 over s squared plus 9 times 1 over s minus 1. And that's it. Sorry about my dogs. The mailman must be here. And the dogs are pretty convinced that the mailman's a terrible, terrible person. So try not to mind them. He'll be gone in a second. Okay. Let's go ahead and compute the Laplace transform of cosine 4t convolved with t to the 5th. Well, the Laplace transform of two things convolved is just the product of the individual Laplace transforms. So that's Laplace transform cosine 4t times the Laplace transform of t squared, or of t to the 5th. Alright, Laplace transform of cosine 4t is s over s squared plus 16 times the Laplace transform of t to the 5th, which is 5 factorial over s to the 6th. And that's it. Okay, let's go ahead and compute some inverse Laplace transforms. This one, again, you could do partial fractions. I'm not going to do that. What I will say, this is the inverse Laplace transform of 1 over s minus 1 times 1 over s squared minus 4. And you know how to inverse Laplace transform each of those individual parts. So you could say that this is the inverse Laplace transform of 1 over s minus 1 convolved with the inverse Laplace transform of 1 over s squared minus 4. And that is what? This one would be e to the t convolved with 1/2 sine 2t. Right? Okay, and also, so this one's the same thing, right? I could say this is two things multiplied, s minus 1 over s minus 1 squared plus 1 times 1 over s minus 2. So this is the inverse Laplace transform of the first one. Convolved with the inverse Laplace transform of the other one. Okay, the first one takes a little bit of work to inverse Laplace transform, right? This is the inverse Laplace transform of, this is s over s squared plus 1 shifted by 1. It's an inverse Laplace transform times this one. I can inverse Laplace transform. Oops, that's convolution. Sorry, do not make that mistake. This one is e to the 2t. And now we can say, okay, this inverse Laplace transform here is going to be e to the t times cosine t convolved with e to the 2t. Okay, and if you have any questions about how I went from here to here, just go ahead and that's the first shifting theorem. I think that's in section 4.2, or drop me an email, whatever. Okay, let's do one more. I want to compute this Laplace transform. So I'm just going to say the Laplace transform of this integral of f of, well, I mistyped that a little bit. Let me say the Laplace transform of the integral from 0 to t f of tau d tau. Okay. I want to Laplace transform that, and there are lots of ways you can do this. My favorite thing, though, is to say that, look, this is the Laplace transform of the integral from 0 to t f of tau times 1 d tau. And that is, look, I've plugged tau into f of t here. This is f of t with t equals tau plugged in. And here I've gone ahead and plugged, this is 1, but with t equals t minus tau plugged in, right? This is, if I shift the function 1 by t minus tau, nothing happens at all. So it's just 1. So this is really, this is f convolved with 1 here. Okay. So if I want to Laplace transform the unknown function f convolved with 1, well, that's definitely the Laplace transform of f times the Laplace transform of 1, and that one is easy enough to figure out. That's, well, Laplace transform of f, or you sometimes write capital F for that, and then times 1 over s. And that's it. So anytime you want to Laplace transform the indefinite integral of some function, f of t, you get the Laplace transform of f divided by s, is what you should get there. So, okay, let's go ahead and solve some differential equations involving these convolution integrals. So I want to solve this equation here for the unknown function f. Okay, so I want a function f such that f of t is equal to 3t squared minus e to the minus t minus that integral. Okay, so again, the unknown function is f. These are called integral equations because they involve these integrals here. It's not a differential equation. We could convert it to a differential equation, but that's not as much fun. So let's just go with it this way. When you have these integral equations, you don't specify the initial conditions. You can just gather it, right? If f satisfies this equation, then f at 0, so on the left-hand side I'd have f at 0 has to be equal to 0 minus 1, and then I'd have an integral from 0 to 0 here, so this term is 0 also. So f at 0 has to be minus 1. So you can gather that right from the problem. You don't need the initial condition there. Okay, so what I want to do, again, I'm going to just Laplace transform everything. And in order to do that, I'm going to have to recognize this last term here, this guy, is just the function f convolved with e to the t. So I'm going to rewrite my equation like this, right? I'll just say, well, this is f convolved with e to the t. And now I'll just Laplace transform everything. Like always, I'll write a capital F for the Laplace transform of little f, right? And I'll get capital F here, and I get here 3 times 2 over s squared from this term, right? And here I get minus 1 over s plus 1 right there, and minus, and here I'd have the Laplace transform of little f convolved with e to the t is going to be the Laplace transform of little f, which is big F, times the Laplace transform of e to the t, which is sitting there. So you Laplace transform everything just like always. Solve for capital F like this. And yeah, then just go ahead, use partial fractions like always, and then inverse Laplace transform. And you end up with the solution. So that's it. These convolutions are important things. They really do show up more frequently than you would expect, especially if you've taken a class in like probability or statistics. You'll find these convolution integrals floating around. Yeah, they do show up, and this is one way of dealing with them using the Laplace transform. So that's it.